Hi, hope you can hear. Good afternoon, everyone. Can you all hear me? To test. Make a quick test. Yeah, okay, good. I think someone can hear me. So on Monday, I have covered about. Good, thanks. Yeah, may have some delay. But getting lesser and lesser people attending. So, on Monday, I have covered in last week we covered the breakfast search graph, breakfast search, DFS search. Monday I have covered in the DFS search. You will find that the DFS search you have find that the way they visit the nodes, the graph is you trying to. It's kind of a greedy strategy. You trying to visit whenever you find out there's a nodes is available, you will trying to go there. And then whenever you find that there's a nodes, adjacent nodes, which is unvisited, you will trying to immediately visit it. And only until you reach a point, or you can think it's a leaf nodes, or there's no more unvisited adjacent C nodes around, unvisited adjacent C nodes around, then you will do trick, a method is like called backtracking. You will backward, one step backward to the earlier visited nodes and trying to look for another alternate path to visit another nodes. So such a reverse backtrack is known as backtracking. So this kind of a backtracking technique can let us, or yeah, you can let us to solve a lot of problem in our daily life. Like I have mentioned on Monday about the one of it is very typical problem is solving the maze. You want to find out the path. Yeah, you can solve using the backtracking technique to try out all the possible path. Eventually, if there's a path for you to enter at the entry and then exit at the left at the exit, then you definitely can find out through this kind of a depth search and backtracking technique. We also on Monday lecture, I have introduced you a very classic problem about the coloring made by M color, any number of color. I think at least you need take 4 to ensure that you can color different to put different color in different region. Then there's no any adjacent regions in the same color. Is in the same color. So in such a way, you what you can do in on Monday have been tell you that you also can use the backtracking algorithm that you can starting from a initially put one color. The idea is like initially I put one color in one of the region, and then then I look for the next region, next adjacent region, and then put another color and check whether this is valid or not. If it is invalid, I will do the backtrack and then try another color, try another color, try another color. If it's no color I can put in this region, I will backtrack and backtrack and backtrack. Every time I will put a color, and then there's a key is I need to validate. The key is I need to validate whether this is a valid assignment, color assignment or not. If it's valid, then I carry on. If it's invalid, I will do the backtracking. Yeah, because today I'm going to talk about another very classic computer science problem, which is the n-queen problem. Yeah, this is the implementation for coloring. So well, I provide it to you is because it's also can easy find online. Then but the thing you need to learn from it is I mentioned that you'll put a color in one of the region, and then you check the validation. You check the validation. You check whether it's safe or not. Yeah, it's safe or not. Then if it's safe, then you will carry on. Then every time you will keep repeat this process until all the region is fill out the color. So you can see that this one there's a for loop, then with a recursive function inside the for loop. And I've mentioned on Monday, you expect that this one, the time complexity is very high. Similar things you will see in today's lecture. I will introduce another one called N-Queen. N-Queen problem or N-Queen. N-Queen problem is a very classic, but people study about N-Queen. They're saying that it's not limited to 8 only. You can think about 10 by 10, 20 by 20 chessboard, and then how to put 20 queen on a 20 by 20 chessboard. But the solution are exactly the same. The number is not important. So I use an 8 queen problem as an example. If you have a chessboard which is 8 row by 8 column, 8 by 8, you have 8 row and then 8 column chessboard. Yeah, and you know that queen in the chess can move horizontally or horizontally, vertically, and diagonally. So your objective in this problem, you want to put 8 queen on the board, 8 queen on this 8 by 8 chessboard, and then you need to ensure that there's no any queen can attack each other, any other queen in a move. One move I cannot attack any other queen. And then this is the basically this is the problem lah. So the most silly way to do is just try out all the possible combination. You got 8 by 8, that means you got 64 position. You can put a queen. So you can put 8 queen. So it's 64 choose 8 position. The number of permutation is 4.4 billion. That means if you do that means you try out 4.4 billion way, which is, this is just 8 by 8. Yeah, when you go to 10 by 10, it's 100 C10, which is much higher. So of course, this is not a very smart way. Very soon you will realize that not possible that can put the queen in the same row or same column, or diagonally put all 8 queen diagonally. All these cases are not make sense. Not necessary to check. For sure it's not working one. So if you want to eliminate all these cases, a little bit smarter way is, okay, I would like to only investigate the cases is like each row you only put 1 queen. So that means in the first row I got 8 position to put 1 queen. One of the position there's I can put one of them in. Then in the second row I only left 7 possible case. Then in the in the third row I got 8, 7, 6 possible position, and so on and so forth. So the total number of combination is 8 factorial. 8 times 7 times 6 the combination you can have is, you reduce from 4.43 billion to 40,000. Okay, improvement is a lot. So yeah, that's why you have a better algorithm, can save you a lot of time. That is not you buy a most expensive computer can help you to resolve such an improvement. You can see 4.4 billion improved to 40,000. But the queen is like, can we do it even better way? Is there any better algorithm? That's what we always think about it. So if I put one row, is it I really need to test all of them? Is a problem. You put 1 queen here in each row. If I said row, that's mean this one, I put 1 queen. That's it, I only have 7 position I can put. Definitely not here. So, but actually this one also not necessary to test. You definitely cannot put the queen here. You're supposed to test from here. Yeah, if your queen put here, you definitely cannot put the next queen in these 2 position. Yeah, so probably there are a better way to do it. So that is using the backtracking algorithm. So to do this, okay, to illustrate the idea, I instead of 8 by 8, because that will take a lot of time, I use a 4 by 4 to illustrate the idea. So here I reduced, I simplified to 4 by 4 first. But it's the same thing. You can expand it to 8 by 8, 10 by 10. That's not an issue. So starting, I place one queen on the top left corner first. I try this possible scenario. And then I place a queen on the second column and move her until a place is safe, which is a safe place, means that where the queen cannot be hit by the first queen, the queen you put in the first column. And then I carry on. I put the queen in the third column, but I not try all the combination. I will check the position whether it's safe for me to put or not. If it's safe for me to put, I will put it there. Yeah. So and so forth. If you're doing that, definitely there's a, let me try this way, the idea behind. As I said, if I put a queen here in the so-called first column, top left corner, then I put the second queen in the second column, and place it where it cannot hit. Right now only one queen. So this queen you definitely cannot put here. You cannot put in the first place. You will attack by her, sorry. This one also cannot. Then you only can choose here. It's safe. Yeah, you won't attack by the first one. Then you try the third one. When you try the third one, in the third column, this one cannot, you will attack by him. This one, these three, you definitely attack by the second one. Sometimes you even will be attacked by the first one as well. So in that is a circum system. When you reach a scenario that there's no place for you to put the I queen at the I column, then you need to do the backtracking. That means your earlier step is not correct already. You need to find the alternate path. So that is what I means in the line 4. So in that case, that means I need to backtracking. So I need to remove this. This is not the right solution. I need to find the next alternate. So that means that if there's no queen, the program will backtrack and remove and move to the I-1 queen. And then at the I-1 queen is at the, yeah, so we will try another alternate one. So we will try to put here. Then I think this one, in this case, I still can put here, the third column. I carry on. So I will backtrack and then I'll repeat the step 2 and something like step 2 and step 3. I keep carry on to find the safe place to put the third queen. I think this is the good place. I cannot attack by him. Then the last one, again, the last column, I cannot put here, which means that this is not the good place. I have to move. I have to do the backtracking again. I have to book the backtracking. Then, but if you look at it, the next location, this one also cannot. The next one also cannot. Then in that case is what my Wi-Fi saying. If the I-1 queen is at the end of the column, then that means this one also cannot. Then you need to further move backward, backtrack to the I-2 and so on and so forth. So in that case, you have to backtrack to this one. Eraser. Yeah, this one also need to backtrack. However, this one is already at the end of the column. That means you move, no more option. That means the very first one you cannot put in the in the top left corner. You have to try another one. Where's my pen? This one need to try here. And then this one cannot, you try here. And this one you try here. Then okay, in attack. Yeah. Then this one cannot here. I think can put here. Yeah. So if the current column right now is the last column, and you are safe to put the last queen into the chessboard, you found the solution. So that is the solution. So first I tried just now earlier, I tried this, cannot. Then after that you do the backtracking. And then you try the next one. Backtracking, then you try the next location, which is this one. Then you put the next queen. Yes, there's a place for you to put the second queen. Then yes, there's a place for you to put the third queen safely. So same thing, you look at it, it's very similar to the coloring problem. They are using, although look like these two problems are unrelated, are totally independent, but the strategy they are using are very similar. You are using the backtracking technique. So if this one is safe to put, then you carry on to put the last one. And you check, and all the queen, you just need to put 4 queen in the 4x4 chessboard. Then now you successfully put 4 queen. That means you found the solution. And if you just need one solution, yes, you can stop here. But just take note that this may not be the only solution. I think I can try to see. If you try to carry on, maybe this is one solution. If I put the queen, if I carry on, just now this is one. After you found one solution, you can, of course, I cannot put the next one here. I can backtrack. Backtrack means that this one backtrack to here. I carry on. If you stop here, then you found one solution only. If you want to find all the solution, then you need to carry on. I still can carry on. This one cannot. This one I cannot. This one also cannot. Then I further backtrack. This one no more. Then I try. I think there's another one, which is if I start from here, I can put 1 queen here. Then I can put this one cannot, this one cannot, but here okay. Then should have another one is put here. So this is actually another solution. So you can find out that there are several solutions. If you keep carry on, depend how you write the last one. When you place the last queen into the chessboard, is a solution is found, but doesn't mean this is the only solution. So for example, if you try 8x8, if I remember correctly, should be 92. There are 92 solutions. If the you can examine all the possible configuration. Then until you terminate until all the solution is found. You keep trying all the possible configuration which is safe to put 8 queen into the chessboard. You will find that total there are 92 pattern, which is fulfill to place 8 queen into a 8x8 chessboard, and the queen cannot attack any other queen in one move. Okay. So for just now, 4x4 is the one I show you, only 2 solutions. And 5x5, there are 10 solutions. And then 6x6, only 4 solutions, and so on and so forth. The interesting why this problem is very well known in the n queen problem is like, placing the queen is the solution using backtracking. Not, I think it's quite clear. People find that actually you notice that this number of possible solution here, the pattern is not clear. When your problem size is increasing, yes, the number of possible solution is also increasing. But if I'm not wrong, right now people still haven't found out the how to calculate the number of possible solution. Yeah, you can see they grow you expect it's exponential, but you don't know the exact they can't find the is 2 power to n is exponential or factorial or what. Yeah, this is what some people are studying. Yeah, or some people may trying to improve the backtracking algorithm. So that end up this problem is so well known in computer science. Yeah, correct that to set the DFS will always try to find the you can think that okay, DFS is a kind of a greedy strategy. It's a kind of a greedy strategy. In such this kind of a problem is very suitable for you to find to use a DFS, to use a depth first search or backtracking to search the solution, because it's always once this is a possible one of the possible, like what I mentioned on Monday, once this is a possible choice, you will just put it and try to move on and move on and move on. Then if you reach the goal, your target goal is put at queen, then you will stop. Then you don't a lot of time we just need one solution. We just need to have a solution on it. We don't really need to know all the solution. Then if that your problem is something like this kind of a greedy strategy is very suitable. Yeah. So we'll always try to find a quicker solution. I would say it's a kind of a greedy strategy. I don't want to use it may not be the faster one, or yeah, because sometimes you may find that trying to try some path is not valid. Then you need to go through all the path which is not correct, but you have to backtracking and try another path. In this kind of a problem, it look like yes, it is lah. But in some other problem, it may not be. But you can see that it's like at the moment when I put one queen, I want to look for the second queen. At that moment, I only can put I only know how to put the second queen in the second column or second row. I don't really know that at that moment, I don't really know that whether this arrangement is the best solution or not. I have to try and check, verify it. If you don't try, you won't be able to know. And you don't know you don't bother about other possible solution. You just greedy strategy. If this one can be a possible solution, you will just use it and move on and move on and move on. If you're successful, you put at queen, that means you found the solution. You can stop it. So that is kind of a greedy strategy. So is it same to say that it find the first solution, but it does not have to be optimum? It find the first solution. It can be it may not be optimum, because you are usually this kind of a greedy strategy. You only at the moment you imagine you are in a graph, you stand in the one node. At the moment you only can see your adjacent nodes. You don't know how big the graph it is. So at that moment you always choose this kind of a greedy strategy. Is like you only choose the best you can do. You only look at your adjacent nodes, which one you can go to. So you choose the one you can go. But that particular path, you can see that just now when I try the 4 queen, initially actually I think initially I reached certain point. It's not, but before that I don't know. So it may not be, maybe can set it's not optimum. This is not the optimum, or this is not the right solution. But at the point I put the first queen, I cannot guarantee this is not. Only after I put 3 queen, I realized that it's not possible to place the queen in this manner. Then I then I need to find the alternate solution. So because it's at the moment you place the first queen, you can place the first queens here, but does not mean that this is definitely the best solution or the correct solution. That's a lot of time you face in those puzzle. You can make a decision on that, but the decision you make may not give you the optimum solution or not the best solution. Then you always need to try to correct it and find the alternate one until you satisfy certain condition, like placing 4 queen here, or like earlier you coloring, you check through the whole mat, there's no any adjacent mat having the same color, then you satisfy this condition, this objective, then you solve the problem. But at the time you color the first region, is red color, blue color, yellow color, you don't really know that this is the solution or not. You only can move on and fill out the rest, then you can judge. Yeah, so it may not be the most efficient one, but you will find that this kind of a problem, yeah, probably you have at the moment you make decision, you have no choice, because the information you have is all the adjacent nodes around. You only can check the adjacent nodes around. If you want to get the optimum, then you need to, every time you make a decision, you need to understand the whole graph to make a decision. You also find very tough and you will find very difficult. So since it's that case, yeah, why not just use a greedy strategy based on the nearby. The best decision I can make at that moment is just check the current column. Yeah, whether I place a queen in here or there, is it okay or not? When I make color a certain region, I just choose the best one I can choose. Yeah, you can see that when you color, for example, back to the Monday problem, when you color the first region, you can put all the color you can put. So all the color are possible solution, but you don't know which one is the best, or so-called which one is the optimum. Then what you can do? No choice. Just try one first. Just try one. Red color, how? Blue color, how? Yellow color, how? Then you move on. Only you move on, you know this is a solution or not. Yes, it may not be efficient, but you find that it's not efficient, but it's an optimum solution. Probably is one of the optimum solution, or it's the only way you can try. Yeah, but you systematically try it. But I systematically try it, so I will miss out the solution. Okay, so that is roughly what the backtracking we use. It's kind of a greedy strategy. So what is the different use case? So you back to breakfast search is not. Breakfast search is level by level. So for this kind of question, if you really use like level by level kind of a strategy, that's when you keep trying, you move one step, you know that, okay, this one you want to do it. It's something, I don't know, can I use a breakfast search here? Some question actually sometimes can, but sometimes can use breakfast or breakfast. In the matching problem, I will discuss next week and next weeks. Yeah, you will find a yes. But for here, I think it's like this one, breakfast search is something like, yeah, I can choose this, I can choose this, I can choose this. I build a big graph. I can choose this. Imagine that I have a graph start from nothing. Then I can place queen here, I can place queen here, I can place queen here, I can place queen here. Then I can place queen. Then it's like you're trying to level by level, you move, then to find all the possibles, like scanning level by level, you're scanning all the way till the end. Then you find valid or invalid, valid or invalid. Can you place a queen in this path or not? Then I think that is kind of a breakfast search, but you can see that you get one but if your objective is you just want one solution, it give you all the solution. I think it can, in the end you can know all the solution, but the computational time is you need to try out all the cases. That first search is just try, then backtrack. So once you found one solution, you're happy, then you can stop already. If you are happy, you can stop, right? if that is the objective, then breadth first search will be better. Breadth first search, I think if I want to know all the possible solution, probably I can use the breadth first search also. Yeah. So both are actually is a path, can let you search the path, but breadth first search you cannot halfway found one solution. You have to move on. I think I cannot think out a way to find one of the solution by using the breadth first search. Yeah. But breadth first search can let you do is like, I think in this week tutorial, if you use the breadth first search, I think one of the question, you will learn that actually it can tell you the shorter path. Like earlier, I think the first problem I discussed about the maze. If you use the breadth first search to solve finding the path of the maze, it can give you the shorter path. He can tell you the shorter path, but depth first search only give you a path to get out from the things, but it may not be the shorter path. But you find that if you use the breadth first search, you will take more times. Yeah, and theoretically, you will take more times to find the path because you will try out all. You will it's a level order, so it keeps slowly scan the network, the graph to find out all the possible path from A to B. It not only find A to B, it's A to any nodes. Then eventually you'll find the shorter path from A to B by breadth first search. Depth first search is like they keep trying, backtracking. Whenever you from A to B, you reach B, you stop, you found the solution already. But that solution may not be the best one, may not be the shortest one. But anyway, it's still a solution. Depend your problem. If you don't mind the distance is not the shortest, you just need to get out from the maze, you can choose depth first search. But if you really want to find the shorter distance, then probably breadth first search is the best. Okay, so that is the n-queen problem. So in short, yeah, this is I think the next week lab I will ask you to try to implement it. But this question I would say is quite classic, so that's why I don't want to put in the assignment. You definitely can easily find the algorithm, the code online. Yeah, so it's I give you the pseudo-code here. So you let's say you have n by n. So here is a 4x4, easier for me to illustrate. So as long as you can see that's very similar to just now the coloring problem. There's a for loop. Definitely there's a for loop inside because you need to try all the possible position in that particular column. You need to try out all of them to check whether they are safe to place it. Earlier, maybe you can compare the earlier one, the coloring one. Yeah, I should put in the next slide. Yeah, this one you can see that you try different color. You run a for loop, is try out to coloring the different color on the vertex. You try this color, this color, this color, whether it is safe or not. Then n-queen problem actually is very similar. The algorithm is very similar. Okay. Yeah, here. You're trying all n by n. So you try, as long as your column is greater or equal, as long as you still, yeah, you try, you haven't reached you still try the first column, second column, as long as not the end column, as in you have to move to this part. Then you will try let's say the first column, when your column is equal to 1, when your column equal to 1, when your column equal to 2, it should be, I think I start from 1 to n. So 1, 2, 3, yeah, as long as not more than n. then you will carry on here. So then you'll try this one. Yeah, whether you will try, the for loop is trying to try from here all the way to here. Then every time you try one position, you will try to check whether it's safe or not. Just like the coloring, you try, this is the right place to put a queen or not. So you probably will use a separate function to check is true or not true. Is safe to put a queen here or not. If it's safe, if it's true, then you place a queen. Then you will recursively call the same function, the n queen problem, for the next column. So your column just +1. You keep doing this, then until you reach the last column. However, if it is not safe, then if it is not safe, that means that you reach certain column, you run n iteration, you run through n iteration, which is not safe to put. There's no any possible position for you to put a queen in that column, then you will return false. If you return false instead of true, then when you return back to the earlier function call, that means it's something like backtracking. You backtrack, then you will delete the queen. Just like this. You find a queen, you run a for loop to test the second column, you place a queen. You go to the third column, you go to the third column, you run the for loop, recursive call third time already, recursive call second time. First time you place the first, initially you call this function, you place the first queen. Then, so the next recursive call, when you go here, your next recursive call, then you go to the second column, then you place the second queen. After the for loop run 3 iteration, you found that the queen can place here. Then you recursive call this n queen function. You go to here, cannot, here cannot, here cannot. So cannot put any queen in any one. Then you will return false back to this place. Then you will delete the queen. Yeah, this step is delete the queen. When you delete the queen, then you carry on your for loop. You will try to put a queen here. Your for loop not yet. In the second, in this particular call, yeah, after you delete the queen, your I is still less than n. You still can try. Still got one more position to try. Then you carry on. Then check. Okay, it's safe. It's safe. Then you place a queen. Then you will recursively call the next column. Your column +1, you will run the recursive function. Then you place a queen. Yeah, this time can place a queen. But then you will recursive call again. Then recursive call go to here. Then this one cannot. Then you will backtracking. Then you will return false. When you return false to this earlier function call, then you will go to delete the queen. So the third column queen deleted. And then the for loop for the third column, you still carry on to try to put at this position, cannot. This position is not safe. Then again, you will return false to the earlier function call and then remove the one. Then this one also no more already. You already try out the for loop already finished. So you only can return false to the first column. Then first column also need to remove and then try the second position. Yeah, repeatedly do this. Then you found the column. Once you reach the last column successfully, only when you reach the last column, then you will return true. Then everything return true. Then if you return true, then you will return true. Then you will return true. Will return true. Then you will eventually you can return back true to the main function. Then solution found. Okay, so that is the in fact it's not only add queen, like n queen problem. Depend my board size, I can use any number. So you can see that every column I place one queen, I try all the possible case. So worst to worst is definitely less than 40,000. So please show helper function. You just check is safe or not, no? So when you check is safe, that means this one helper function, you can see that what I need to do. Let's say you pass me the board with the queen. I just need to check that I want to check whether I put, that means what does it means? Today I want to, that means this part you expect that you need to write, yeah, you need to write whether it's safe or not. If I want to check whether it's safe or not, that means that when I check this one, I need to know all the earlier arrange. When I go to third column or any column, I need to check the chessboard. You need to provide me the chessboard, and then I need to check whether I can put in the IJ position on the chessboard. Is safe is just like you pass me the chessboard in the current arrangement plus the IJ coordinate. Then that particular function will check horizontally along the I. Any queen is already there. If not, then safe. Then you check diagonally. Yeah, along here. That means one is check the I. If along the I, along the J, then along this one is the, you expect that this, then you can observe zero. That's it. If I start from, if it's using C, then I will start from 0, 1, 2. So this one the coordinate is 0, 1, 2. This is 2. Then 2, 0. Then this one is 1, 1, 1. This one, of course, this one is the one IJ, the IJ, which is 0, 0, 2. Then the other one is 2, 0, 1, 1, and this one will be 1, 0, 1, 2, 3, 1, 3. So if you can see that if I plus J, the given coordinate, then and then I need to check all the position, their I plus J, their index I and J, I plus J are equal. If I plus J equal to 2, I plus J equal to 2, and there's a queen in that location, that means you cannot place a queen here, right? Yeah, so you need to check all the direction. Got it, all direction are checked in safe. Yeah, so that means you need to write such a function to check whether it's safe or not. That is the function you need to write for this part, for this one. Yeah, that will be talk about it next week lab. I think next week lab, the last question, if I remember correctly. Okay, so yeah, that is the backtracking, one of the quite useful trick. You not only can solve the maze, color, and queen problem. Yeah, in fact, Sudoku also can, because you can see that you put one number here. If you know what is this is the Sudoku. That means you try you from here horizontally along here, then on and the 3x3 grid, you only can put 1 to 9 So you already put 5, 6, 8, 4, 7. That means I can if I check horizontally, the option I can put is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 9. Then you check vertical. Yeah, so you only can put, it's safe to put this number if you check vertically. Then it's safe to put what you can eliminate. I think 9 you already cannot put. Then 3 also cannot put. You only can put 1, 2. So you can eliminate. Then among them, then which one you can put first? You're trying to put. If you only one choice, you can put. I think the Bullfrogs depends how I design. I probably will find those only have one possible choice. Then I will put those first. Then if not, then I will try to put one number first. If cannot, then later I will backtracking. I will backtrack. I try another number. Yeah, so this is obviously you can see that actually you need to use the backtracking algorithm. It's another very classic problem which we need to use the backtracking algorithm. Otherwise, if you brute force try all the combination, the combination is a lot. So that is Sudoku. And then another one is Hamiltonian cycle, also can be used the backtracking algorithm. So it's a path. Hamiltonian path is a path that visit each vertex exactly once in an undirected graph. That means that this one can be visited once. Yeah. Is it only here? Yeah, only this one. Only this way. Oh, okay. There's another one. There. Only another way can be here. A path that visits each vertex exactly once in an path. If the last vertex has an edge back to the first vertex, then that is the Hamilton cycle. I think this one, then this one. I think the correct one should be, let me erase it. Should be this one, this one, this one, this one, then back to the first one. Then it's called Hamilton cycle. So that this one from this particular cycle is from the Hamilton cycle for this particular problem. Yeah, of course, this one is not. This one is not. If you travel in this manner, is not correct because this nodes is visit second time already by doing so. Yeah, so you of course this is a simple example. You use your naked eyes, you can judge. But when you have a very complicated graph you want to visit, then what you can do, you can use a backtracking. You try this path, cannot, then you find that you need to repeatedly visit the same nodes again. Then you will backtrack and try another path, try another path, try another path, until you able to visit all the nodes once and you back to the first vertex. Then that is a Hamilton cycle, because Hamilton path is visit each vertex exactly once. Then cycle is Hamilton cycle is like the last vertex has an edge back to the first vertex and have an edge for you to back to the first circuit. Yeah. So that is Hamilton cycle. Yeah. So to do that, you expect that also can use the backtracking algorithm to solve the problem. Okay. So backtracking is trying all the. In short, you can find that whenever this kind of a problem, you want to try all the permutation, but you do not. If you really try out all the permutation, the cost really very high, and then if you use the backtracking, doesn't mean it's better. That's why I said I in the end I conclude it's not really a very smart approach, but it is a little bit smarter than you really brute force try out all the permutation, because this one can help you to you find that if you can eliminate in the halfway of checking, you can in the halfway you can terminate your searching for certain permutation. That can help you to reduce the search time. Then backtracking can help you to reduce the search time, to reduce the number of permutation. You can eliminate certain pattern of the permutation that you don't need to carry on to check this kind of a permutation, because this portion is not possible a solution. You can stop in the halfway. You can try another the rest. You just need to try the rest. Can help you to reduce the number of cases to investigate. That can save you a lot of time. But it still may not be the like what's just now discussed, that it may not be the best one. This may not be the best algorithm. Yeah. So it's a little bit smarter approach, but not the best. But at least you can solve the problem. This is a very typical greedy strategy, because you don't know everything. when you make a decision at that moment, a lot of time you only look at the next column and make a decision, or you look for the next region, you make a decision. You visit the next vertex, or you in the maze, you just move the next available step you can move. You just try to move in that direction first. So all this is at that point, that is the best you can do at that point, but doesn't mean that is the best solution. Yeah, but no choice, you don't know. You don't know whether if you don't try, you don't know. Then probably that a lot of time that kind of a problem, unless you really want to try all the permutation, not smart. At least I try this way, I can save sometimes. Yeah, I don't need to try some unnecessary permutation, which is already at the beginning. After 2-3 steps, I already know that it's not possible. Yeah, so it can improve the algorithm compared to the brute force, but it may not be the best. But sometimes you will find that, yeah, we probably won't be able to find an even better way to solve that kind of a problem already. This is so-called the best we can do. Yeah, so the one I think tonight I probably will release it, the assignment. Okay, so I think I will end the lecture today, but next Monday I will talk about, just let you know, give you a quick overview about the next week lecture. That is another topic I would like to talk about, is a dynamic programming, something related to backtracking also. So dynamic programming, okay, maybe I quickly highlight this. Take notes, although they call dynamic programming, but they're actually not really the programming like what you taught. It's not programming, it's not a programming language. The term programming is referred to a tabular matter. Actually, it's filling the table in short. Yeah, and it's a kind of a optimization problem topic. There are a lot of this kind of a programming in the mathematical optimization. I think probably in the SPMS maybe have some courses teaching linear programming, integer programming, convex programming, semi-definite programming. It's all not related to coding. It's a kind of a optimization. They trying to like all this linear programming optimize. I think linear programming I have shown you in the very first lecture also. It's a kind of you have a lot of constraint, and you want to optimize some objective function to minimize certain objective function or maximize certain objective function. Then that kind of a problem is, you need to use the linear programming to solve it. So if it's the objective function is the linear function, then it's a linear programming lah. If the answer, the solution must be integer, then it's an integer programming. And in short, so this one, just let you know, a lot of time people misinterpret, thought that it's a programming problem. It's a programming problem, but it's not the programming, it's not a coding problem you thought. Okay, so it's widely used in like those people learning in the control theory to economy. People are using this optimization problem to solve their problem. Or I would say optimization method to solve their problem. So this dynamic programming, the strategy is very similar to divide and conquer. However, you will find that the problem, when you divide the problem into sub-problem, you will find that the problem is the sub-problem itself, there are a lot of repeated sub-problem. There's a lot of overlap, repeated sub-problem. If you use the divide and conquer strategy to solve the problem, you need to repeatedly do it. Repeatedly do exactly the same problem side, same sub-problem. One of the example, very classic example, is when you calculate the Fibonacci number, which is the Fibonacci you have learned is the n equal to the sum of the previous two terms minus 1 plus the minus 2. which means that you can see why I said this one. If you use the divide and it's something like a divide and conquer, but the difference is like if you have a you can see what is the issue. If your n is equal to 4, then you are trying to solve this problem by you need to solve n equal to 3 and n equal to 2. n minus 1 and n minus 2. If you know this smaller sub problem, these two smaller sub problem, then you know the n equal to 4. But you want to know n equal to 3, the solution, then you need to know the sum. It's the sum of the n equal to 2 and n equal to 1. Then this one is also 1. Yeah, basically it's already the base case. So normally you stop here. And then you will find that actually this kind of a problem is one of the very typical dynamic programming problem. Why? Let me have a color. You can observe that this n equal to 2, you need to calculate 2 times. And actually not necessary. If I do it once before, so that's why I said it's a tabular, is filling the table. So if I have a table, to know that n equal to 2 is equal to what? Let's say it's equal to 1. Then next time I encounter the same problem, I don't need to repeatedly do that calculation again. I just check my table, I can find out the answer. That can accelerate the computation time. Because this thing, you look at it, you need to, now it's only n equal to 4. You can try bigger number. You will find that you need to repeatedly calculate certain problem again and again, certain sub problem again and again and again. Like if you try n equal to 5, I think you will see n equal to 3 several times. Yeah, then why I need to calculate n equal to 3 several times? To accelerate it is like once I calculate the n equal to 3 once, then subsequently if I encounter the same problem, I just check the table. Can help me to accelerate the computational time. If you don't do that, you still use the recursive approach to find the Fibonacci number, you will find that the computational time is in exponential. I have mentioned in the first lecture that you will find that the computational time is 1 square root 5 divided by 2. The proof I think you in the discrete mathematics I think they will cover it, but I just let you know that the complexity is in this level. It's 1.6 something. Yeah, 1 plus square root 5 over 2 power to n. That is the time complexity to compute if you use the conventional recursive function. So yeah, you can use the dynamic programming, you build a table, then can shorten the time. So that is one of the possible approach to improve this Fibonacci number. Is because that you find that there's a sub problem, and such a sub problem, to use the dynamic programming, the key is the sub problem itself that is repeated, appear here and there again and again. Yeah, they are not independent. Yeah, so the sub problem are not independent, means that you need to repeatedly solve particular sub problem again and again and again. Since no point to do that, if I make a table, store the solution there, instead of recalculate the same sub problem, I just use the table to go and check the answer. Then can save me a lot of time. If the problem is independent, all the sub problem are independent, then probably the dynamic programming didn't help you improve anything in the end. The key is they are not independent. Okay, so and the problem usually can have multiple optimum solution. Yeah, you will find but the DP just trying to look for one of them. Like I said, a lot of time we just want to know one solution. Although I know that they have a lot of other optimum solution, but not important. I just want one optimum solution. Yeah. So more details, I think I need to stop here. More details, I will talk about it next Monday and Wednesday. I think I will talk about, yeah, this one and the approach, and also introduce one of the classic problem. Yeah, this one, the rock cutting, next week. Maybe give a quick view. I'll upload this one later. Yeah. So this one is another problem will be discussed on next Monday and Wednesday. I'll upload this one later. I think I already upload the notes in the NTU Learn. This slide I haven't uploaded. Later I will upload it shortly. Yeah. Okay. So this one will be discussed on next week. Any other question? The assignment I will release. So we still have 2 more assignment. One assignment I will release it probably tonight. And remember that the assignment 4 will be, the deadline will be tomorrow. So take note that after tomorrow 11:59, the link will be anytime will be cut off. I will end the test anytime after that. So if you still can log in, you still can submit it. Don't worry, there's no any late penalty. But you don't try to test it, because anytime once it cut off, once I end all the tests, I will not open it again. So, but I will end the test only after 11:59, anytime after 11:59 tomorrow. Okay? So take note, I still can see some people haven't logged in yet. If tonight you don't log in, tomorrow you also won't be able to log in anymore. Yeah, the link will be invalid after tonight. So please take notes. If no other question, I will stop the lecture. Thank you for your attending.